clearly didn't do too well with that. The other is to keep everybody awake. And I'm pretty sure that our next speaker should have no problem with that at all. As undergraduate computer science students, I think one of the cornerstone courses that we all take is databases. And it's an absolute treat to have our next speaker here, because her books probably make it to the recommended reading list of every database course that's out there. Dr. Jennifer Whittam, Lecter Jones Professor, CS and Electrical Engineering, and the Senior Dean of Faculty and Academic Affairs at the School of Engineering at Stanford University, is here to grace the occasion. She received her PhD from Cornell University and was a member of the research staff at Ali and Mohammed research labs before she went on to join Stanford University faculty. She is an ACM Fellow and a member of the National Academy of Engineering and American Academy of Arts and Sciences. She received the ACM Sigmod Edgar F. Codd Innovations Award in 2007 and the ACMW Athena Lecturer Award in 2015. Her research interests include many aspects of non-traditional data management. She's promised a session that's going to be very engaging and interactive, so please let's welcome Jennifer.
Thank you very much. Before we get started, I just want to make sure the microphone is good, because I'm going to just plow through. Are we all good with the microphone? How about in the back? Raise your hand if it sounds good in the back. That's not quite all the way in the back, but way in the back? Sounds okay? All right, let's go for it. So I'm going to tell you about some magic moments in my research and teaching career. And I'm going to start by giving you a little bit of background, because there was a key thing that was missing from the introduction, which is the fact that my bachelor's degree is in trumpet performance. And I am utterly serious about that. So I was a music major, and I'll be happy to talk to you afterwards if you'd like about how I switched to computer science. But I did move from that trumpet performance degree, and I'm not going to play trumpet for you today, don't worry, to a PhD in computer science. I did spend 5 years at the IBM Almaden Research Center, and I've now been at Stanford for a little over 22 years. In addition to traditional stuff, I've been kind of an administrator lately. I was the chair of the computer science department at Stanford for about 5 years, and I currently hold a half-time role as the senior associate dean in the engineering school. Okay, so a lot happens in a 30-year career. I can't cover all of it in less than an hour, but I am going to talk a little bit about research and a little bit about teaching. And the talk is going to divide into 2 parts, maybe 2/3, 1/3, half, something like that. On the research side, I'm going to talk a little bit about finding research topics, how I've gone about that. I'm going to talk about methodology for research, and then I'm going to sprinkle in a bunch of examples. On the teaching side, I'm actually going to focus very specifically on the emergence of what's now called MOOC movement, Massive Open Online Courses, which I was involved in, and I'm going to wind back to the year 2011 and talk a little bit about what went on then. Now, I've called the talk Magic Moments, and I am going to even show you what I consider the most magic moments. So when that symbol pops up, that's a magic moment that I found in my own career. All right, so let's launch in, let's talk about research. I want to talk about how one finds research topics. And I am going to start by stating that I have built my career on not being a visionary. I'm not a visionary. I never think that I know what's going to happen in the future. So don't ask me about 2020. I can maybe tell you about 27. Well, don't ask me about 2030. Maybe I can tell you about 2017 or 18, something like that. So really not a visionary. But I have had a series of successful research projects. And what actually happened in my mind is that I found a recipe for research that works. And this is a recipe that works at least in my research area. My research area is databases and information management. I think this recipe could work in other areas too, not every area. But if you're working in a different area, maybe think about whether this recipe would work for you. Okay, so here comes the recipe. It's a pretty simple one. Database management systems, or database systems, or data work in general, turns out to have a lot of fundamental assumptions built into the way it's structured, the way it's operated. So my idea, a long time ago, was let's pick a simple of a fundamental assumption that underlies a database system, and then drop that assumption and see what happens. And I'll get to some examples momentarily. It turns out that in databases, at least, I think of it as sort of like a sweater or something with a little piece of thread sticking out. And when you drop an assumption, you start pulling that, everything starts to fall apart. You have to reconsider all aspects of database management and query processing. And the good thing about that, when you're a faculty member, is that if you take this assumption, you drop it, and everything falls apart, you get many PhD theses as you try to put things back together. And also, I always like to have prototypes being built in my research group. So we often would build a new prototype, which is a database system where we drop an assumption. Okay, that's all a little bit abstract. Let me get much more concrete. I'm going to give you an example of several cases where we've taken one of these, quote, simple but fundamental assumptions, dropped it, and spawned a whole research project out of that. And these are some examples through my own history of research. So first of all, how many of you have taken one database course? Okay, so a reasonable fraction. Are you hearing me in the back, or you just don't take databases if you sit in the back? Because I didn't see very many hands. How many in the back half of the room have taken databases? Okay, a few. Okay, so I'll try to keep this at a level where even if you've never taken a database course, that you can still understand what I'm telling you about. So in the database system, one of the very basic assumptions is if you're going to store a whole bunch of data in your system and query that data, you need to declare in advance what the structure of the data is going to look like. And I have a few tables. One of the tables is going to have information about students. Every student is going to have an ID, a picture, maybe a transcript. You declare that before you can put any data in the database system. What if you want to manage data and you don't know what the schema is in advance? Or what if the schema is not stable, dynamic? What if it's not consistent? That spawned a whole area called semi-structured data, just dropping that one simple assumption. And we spent quite a bit of time revisiting all aspects of data management and query processing in the area of semi-structured data. Here's another example. You probably think of databases as these stable disk-resident things. You take a huge amount of data, you put it on the disk, it sits there, and then you ask questions and get answers. That's what most people think. But what you drop that assumption, and instead of having stable disk-resident data sets, your data is coming at you constantly. We call that data streams. It actually turns everything upside down. Instead of having the data sitting there and you ask questions, you have the questions sitting there, and the data streams through, and out come the answers to those questions. And just that little flip of how you're thinking about things yields, as I said, many PhD theses and a large prototype system that we built. Another example, you probably think databases contain known values. Here's somebody's salary, here's somebody's office, here's their photograph. What if the data is not so precise? What if it's maybe fuzzy or inconsistent or probabilistic? Drop that and you get the area known as uncertain data, and again, everything changes. Most recently, we've been looking at an area called crowdsourced data. Instead of assuming that all of the data management and processing is done by a computer, what if you mix together the computer and then you have humans involved in the query processing when there are operations that maybe the computer can't do, like pick things out of images or match fuzzy objects. So that's another example. So here's examples of these simple but fundamental assumptions that led to a recipe for a research project. Now what about all aspects? What aspects are there when you need to consider all aspects of data management and query processing? There's the data model. How is the data structured? The query language. How do you ask questions? There's the storage of the data. How do you index the data to get at it quickly? How do you process queries? How do you make the queries run fast? What do you do about concurrency control if there are many people operating on the data at the same time? Or recovery if there's a crash? And how about the application and user interface? All of those are key substantial portions of data management that you need to reconsider when you drop one of these assumptions. So, I'm going to say now, this is the first time I'm going to give you my magic moment symbol. It wasn't exactly one moment in time, but at some point I realized that this recipe was actually working for me. The recipe of looking at databases, saying what are the underlying assumptions, just pick one at a time what happens. And I would argue in other areas exactly the same thing that happens. There are underlying assumptions. They aren't always true. See what happens when you drop them. Okay, I guess I won't take any questions in this venue because it's a pretty large audience. Normally I like to take questions, but I'll just leave plenty of time to take them afterwards. Okay, so that's what I'm going to talk about, finding a new topic. Now let me talk about approaching a topic. So you've dropped an assumption, you've got a new area you're working in. How is that topic approached? And I have rather strong feelings about that, actually. So coming back to the aspects, all aspects of the database system, that's something that you need to reconsider, and I've described these already, but I think it's very important to actually think about these in order. Specifically, one has to not be tempted to start building a system or even designing a query language until you know exactly what your data model is. And by that I mean, how is your data structured? Everybody knows about relational databases. Data is structured as tables. Well, if you're working with graphs, maybe you'd rather have your data model be a graph. If it's semi-structured data, what is it going to look like? If it's a data stream, what is it going to look like? And I'm going to give some examples of challenges just in figuring out the data model. Second, once you know what your data looks like, what's your query language? How are you going to ask questions of that data? And again, I'm going to show that that can be surprisingly tricky as well. And then I'm going to lump all the rest as implementation. Okay? So I feel strongly that you need your data model, your query language, and then you go implement. And in fact, I feel so strongly I'm going to actually separate this into foundations and implementation. And I'm going to argue that it's pretty important to get your foundations straight before you move on to your implementation. You need to do both, and seeing it through to a real implementation is crucially important in a research project. But again, foundations first. And I'm going to go so far as to say I have built my entire research career on taking this approach of looking at the foundations first, and then moving to the implementation and seeing it through to the end. Okay? And that's my second magic moment is, again, not a specific moment in time, but the realization that this is a certain approach to doing research that's worked for me. Okay. So I'm going to say now we're going to get a little more technical. So we've had a recipe for research project. We have an approach that says foundations first before you do implementation. Now I'm going to tell you that that particular philosophy had a dubious beginning in databases. And I'm going to go back to the origins of the SQL query language. How many of you know SQL or SQL? Okay, good. We have a quiz coming up. SQL had, as I said, some questionable beginnings, and here we go. So SQL was meant to be a declarative language. And a declarative language is a language where you say what you want and not how to get it. Okay? The semantics of the language is independent of how you execute it. So when you ask a SQL query, you might say, this is a classic one in databases, I want all employees who earn more money than their manager. So you said what you want. You didn't say, I'm going to do a nested loop, and I'm going to look through all the employees, and then I'm going to probe with their manager and find out a comparison. You don't write that kind of code. You just say what you want, and the system figures out how to get the answer. So that's actually a great thing, and that's one of the key pieces of databases actually, is that it's a declarative query language. The system figures out how to execute your queries efficiently. You don't have to figure that out. So that's great, but not everybody thinks of it that way. For some people, I think the only way they understand SQL queries is to think about how they execute. And I'm going to come to a very concrete example of that right now. So here's our first example. In this example, we're going to have a table T with an attribute A that has values. So it's going to be a table T just with a set of values in it. And what we want to do is we want to decrement the below average values in T. So if something is below average, we're going to make it even lower by subtracting 1. All right, so here's a SQL query that does that. And if you can't read it, it doesn't actually matter. And if you can't read it because you don't know SQL, or you can't read it because you're too far away from the screen, you should still be able to follow. This just says update the table, set A equal A minus 1, where A is less than the average value of the table. That's all we're doing. It's exactly what I said. Decrement the below average values in table T. Okay, here is our original set of values. 4, 1, and 2. Adds up to 7, I'll tell you that. Okay, divide by 3, the average is a little more than 2. Volunteers, shout it out. Well, it's not, or I shouldn't say the answer to the query, but what do you think the values are in the table after we run this update command? 401. Everybody agree? 401. Anybody disagree? 401 sure sounds good to me if it's a declarative language. 401 says, I'm going to find all the values that are below average, okay? And 1 and 2 are both below average, so I'm going to subtract 1 for each of those and I get 401. Guess what? Some of the original database management systems didn't do it that way. They were very execution oriented. They say, okay, I'm going to look at 4. Is 4 less than the average? No, I don't do anything. Then I look at 1. Is 1 less than the average? Yes. So I subtract 1 and I get 0. Then I look at 2. Uh-oh, now I have 6. And 2 is no longer below average. So that is, systems actually did it that way, believe it or not. And I say, whoa, that is very unfortunate. People straightened it out though. So they, at some point, people realized that they were getting execution mixed up with the meaning of the queries. And so, in the end, all systems now will give you 401, like you said. But there's still bad news. Oh, yes, there's still bad news. Sorry, I was skipping ahead. Let me give you one more example on this one, which is that it's even worse if your update says, I want to decrement the above average values in table T. Anybody know what can happen if we try to decrement the above average values? We can get an infinite loop, believe it or not. And this can actually happen in the core implementations because you find the above average value, you decrement it, the average goes down, you have more above average values, goes down, goes down, down. As an exercise, later, why don't you go find initial values that will send that query into an infinite loop or can send it into an infinite loop. Okay, but still picking on SQL, things are actually still not good in the SQL world. And here's an example that is still bad in SQL systems, and you could get Postgres, MySQL, SQLite, and have 3 different things happen with this particular query I'm going to show you. Okay, so in this example, we have a database of temperatures of cities in regions, and we want to get the average temperature for each region. And again, I'm going to show you the SQL code. It doesn't really matter that much. It's a group by query. It says I'm going to group by region, and I'm going to take each region and the average temperature. And here's the starting data. So in the west region, we have 2 cities. We don't care what they are right now, with temperatures 50 and 70. So we will get west and 60. And then in the east, we have 3 cities, 10, 15, and 20. So we will get east and 50. So the answer to this query is west 60, east 50. Okay, all is good. This was not a bad example. The problem is some SQL systems allow you to add the fact that you want a city in the query. Okay? So now it says for every region, give me the average temperature and a city. What do you think the systems do? What does a good system do? A good system says this is not allowed. It doesn't make sense. I've got 2 different cities here. How do I know which one to pick? I've got 3 of them down here. How do I know which one to pick? Is this making sense to people? A little bit? Okay. There's a few nods. Okay, so here's the really amazing thing. Some systems will tell you that you cannot do this because it doesn't make sense because you don't know which city to pick. Other systems will pick a random city. So it'll give you the region, the average temperature, and a random city. And guess what? Another system might give you a different random city, but even worse, the same system might give you one city today, a different city tomorrow, and your database hasn't even changed. And that's because it's executing something, who knows what, and picking out a city, and maybe the database got reorganized even if the values didn't change and you get a different city tomorrow. So I would say still bad news in the SQL front. So I hope I've convinced you that even in very basic databases, query processing and getting the semantics right can be fairly tricky. I'm going to talk, so again, the key is, in my opinion, you need to get your foundations first before you do the implementation. And I would argue with SQL that was not followed, and is still not followed, to tell you the truth. Okay, happy to take technical exactly the meaning of what's going on before you implement it, because again, there's been many areas that are very tricky. Some of the first work I did when I was at the IBM Almaden Research Center was in an area called active rules, which is now called triggers. And triggers in databases say that you can put in your database rules that say when some action occurs, they sit there and they look for actions occurring in the database, they check if conditions hold, and then perform additional actions. So that's what a trigger does. The action is usually an insert, delete, or update. The condition is in SQL, and the action is also in SQL. Okay, so let's go straight to an example. And this is a warm-up example because this one is not too tricky. We're going to have a sales database, and we're going to put into the database that when new sales are inserted, if they're greater than 500, then we're automatically going to give the seller a bonus of 100. We'll just put it in there and monitor everything that goes on in the database. And then we have a second rule that says also when new sales are inserted, let's check the total sales, and if they're greater than 1,000, we'll increase all salaries by 10%. Okay? All right. So now let's say we put in the database, Mary sold 600, John sold 300, and Mary sold 400. All right. So if you look at our triggers, Mary put in a sale of 600, so she's going to get a bonus of 100 for that. And in addition, after the third sale, the total has gone over 1,000, so Mary's going to get a 10% raise, and John's going to get a 10% raise too. Those are our two sellers. Okay, so that's pretty straightforward, but it turns out that triggers can be very, very, very tricky. And here's just one tricky example. This now, I made just a couple of changes. I said, when new sales are inserted, if they're greater than 500, give the seller a raise, okay, of 100. And when new sales are inserted, if total sales exceed 1,000, increase all salaries. That one is unchanged. But I've also changed what happens. So Mary sells 800, John sells 300, and Mary sells 600. Okay, so there are many questions to ask of what would actually happen when you run this thing. How many raises does Mary get? Does she get one every time she sells more than 500 or only one time? How many times does everyone's salary increase? Because the rate, it went over 1,000 here, but then it goes over 1,000 again there. They get multiple raises. And furthermore, if Mary is getting a 10%, which of her salaries does that 10% apply to? And you can answer these questions in any way. So I'm going to just argue that what we really need to do is figure out what we want the answers to be and have an understandable semantics and understandable foundations before you go to the implementation. And now I'm going to tell a little story about different approaches to this very particular problem, which is the problem of understanding how triggers work in database systems. And it's also going to tell a little story about my early career as a researcher. So, as I mentioned, I was at the IBM Almaden Research Center for the first 5 years after my PhD. That's a picture of the IBM Almaden Research Center, nice place. And there I am in my younger days. And I was supposed to figure out how to put a trigger system into the database prototype that was being built at IBM Almaden at the time. So that was my job. And I actually have a programming languages background. So I came there with my programming languages background. I said, okay, I'm going to sit here and I'm going to think about the meaning of these triggers before I start implementing them. Transition tables capturing what changed, conflicts between different triggers, confluence, like if you do them in different order, we would still end up at the same place. I was sitting there thinking about that. And then there was this guy there named Bruce Lindsay. Anybody know Bruce Lindsay? Well, if you look, he's a scary-looking guy, and he would actually stand outside the door where I would go in every day. He's smoking a cigarette, and we're allowed to smoke inside. And he would constantly be asking me whether I was implementing yet. So he was just yelling, it's time to write code, stop thinking about those foundations. And then it was even worse, because across the San Francisco Bay at the University of California at Berkeley, there was somebody named Michael Stonebreaker. Who knows that name? So he's a Turing Award winner, and he was working in the same area. I was brand new PhD. He was a super famous guy, and he was working on exactly the same thing. So he was working on a trigger system for the prototype they were building at Berkeley. I was working for the one at IBM. And while I was thinking about theory, and this guy Bruce was yelling at me to write code, he announced we finished our trigger system ages ago. Okay, so then here comes the magic moment. I said to him, yeah, approach to research was, I'm going to just implement something, and when I want to know what it does, I'll just run it and check, where I was taking a very different approach of knowing what we wanted it to do before we started the implementation. And I've stuck to that approach forever. Another tricky area, data streams. I mentioned that we worked in the area where we're looking at flipping the model and having the data streaming through with the query sitting there and looking at the data and producing answers. I'm just going to give a couple of slides on this area to show another example where things are tricky. Let's suppose we have a data stream that is a stream of measurements from a temperature sensor. So you have a temperature sensor sitting there and sending out data, periodically measuring the temperature and giving a timestamp. So at 4 o'clock the temperature is 72, at 4:15 it's 74, and so on. And then when we run a query, we call it a continuous query that says at all times, I want to know the average of the most recent 3 readings, okay? So this is at any time, just keep telling me whenever there's a new number that comes out, tell me what the moving average is. It's just a moving average of 3 readings. So I think we can figure out what the answer would be as these numbers streamed out. The first 3, we get 74, then we get another reading, the 7 o'clock one, and then the average is 60, we get another, and the average is 64.7, and so on. So that's pretty obvious, that's what you want your query to do. But things get a lot trickier, actually, in this scenario, where for whatever reason, your sensor gave you 3 readings at 4 o'clock. They were in this order, they all said 4 o'clock. So 72, 74, 76, all at 4 o'clock, and then there's this huge blip, and then you got the 3 readings at 7 o'clock, okay? Same query, what do we want the average of the most recent 3 readings to be? Well, you can get different answers, and I'm sorry to say that 2 of the mainstream data prototypes get 2 different answers for this. Now, it's not quite as bad as the SQL story because it's recognized that these different systems made different choices, but they did make different choices and get different answers. One system says, I'm going to get the same answer as before. I've got this list, they came one at a time, and I'm going to keep getting the most recent. The other system made a different decision and said, when I get a bunch of things with the same timestamp, I'm not going to know what order they are. I'm going to assume I don't know what order, they're just going to be a big lump. And therefore, that system would just give you 2 answers, one for the 4 o'clocks and one for the 7 o'clocks. And again, the main point here is that it's pretty tricky and it's easy to get tempted to think you know exactly what something should do on every case, and then you come to a case where it's not so obvious. Okay, so another sad story. Now I'm going to get to the last area and the most technical example, and there will be one really tough question for the audience here. We'll see if anybody gets it. I'm trying to think of what I can offer as a prize for someone who gets it, but it's going to get fairly technical. Like I said, if it's too technical, just shut out for 5 minutes, and then we're going to get very untechnical afterwards. So this area is the area of uncertain data. And we're going to look at an example where we're trying to solve crimes with a database. Okay, so we're going to have a database of information about crimes. We're going to try to generate suspects. And so we're going to have a table that lists cases where there was someone who was a witness and saw a car at a crime. Okay? And then we have another table about who drives what kind of car. So if we want to generate suspects for this crime, we can just combine or join the 2 tables. And we're going to say someone is a suspect if they drive a car that was seen by a witness. Makes sense, right? Someone drives a witness saw an white Acura and someone drives a white Acura, we're going to say they're a suspect. We don't know if they committed the crime. Okay, so for those of you who know relational algebra, this says that the suspects are people who are in the join of those 2 tables. You do not need to know that to understand everything I'm going to say. Now, here's where things get interesting. What if this data is not certain? What if we have witnesses saying, well, I might have seen a car, I'm not sure. Might have said, or I saw a car, I think it was a Honda or a Toyota, I'm not sure. We don't know who drives cars. So if this data is uncertain, then we also will have uncertainty in the answer. All right? Okay, so let me tell you a little bit more about uncertain databases. So abstractly, an uncertain using alternative values and using these question marks. So I'm going to give you these descriptions right now concretely. We're not going to have confidence values or probabilities, although we have them in our project. So concretely, we have this table called SAW, and it has two tuples. Kathy saw a Honda, Kathy saw a Mazda. We also have Amy might have seen an Acura. This question mark says she might have seen it or she might not. So this one has four possible tables. Kathy, Honda, Amy, Acura, just Kathy, Honda, Kathy, Mazda, Amy, Acura, or just Kathy, Mazda. And similarly with the drive, there's a Honda that's driven by Billy or Frank. Okay? How many people are still with me? Okay, good. So you're all eligible to answer the tough question that's coming. Here comes the dilemma. This model, or this way of representing uncertain data is not closed. And what closed means is that when you have a way of representing data and then you do queries on it, you can represent your answer. That's what closed means. The problem with what I just described is that we can run queries, simple queries, on the data I showed you and have no way to represent the correct answer. And here it comes. Same one over here. Kathy saw a Honda or a Mazda. Amy might have seen an Acura. I'm going to tell you the second couple is going to matter and what we're going to do anyway. And I added a couple here. There's a Honda driven by Billy or Frank. Jimmy drives a Toyota or a Mazda, and Frank drives a Honda for sure. And now we're going to generate our suspects. So we generate our suspects as a reminder by joining the two tables. So for example, Kathy's Honda was matched with Honda Billy. And that would be a combination, and that would say that Kathy and Billy are, that Billy is a suspect. By the way, as an aside, anybody notice anything about my choice of names in the example data? That's not the hard question, that's the easy question. Anybody? All the witnesses are women and all the criminals are men? Nobody noticed? Right. It was just subconscious, I think. Okay. All right, so now we're going to generate the suspects, and here's what's going to come out. We're going to combine these two tables, and we get that Billy or Frank are suspects because Billy or Frank might drive a Honda, and Honda might be the scene. Jimmy might be a suspect. Hank might be a suspect. This table has a set of possible instances, right? For each tuple, this one could be Billy or Frank or nothing. This could be Jimmy or nothing. This could be Hank or nothing. This table does not correctly capture the answer to that query. This is my hard question. Can anybody articulate why this table does not capture the answer to the query? Anybody raising their hand? Someone, take a stab at it. All right, we got one. Yes.
Now, I think there's a relation between implicit belief that they are related to Honda.
Sorry?
If we focus on Billy or Frank,
Yep.
they are focused on, they are associated with Honda.
Right.
On the other side, if we focus on Jimmy and basically on Toyota or Mazda,
Right.
but there's no exact relation with the other table that we can see here. I guess.
Okay, give this guy a hand. Good job. Is your chapter also in the best student ACM? Yes, it's a good day for you. Yeah, so the issue here is that there are some correlations between the data here, and that's not captured in the answer. If we have Billy in the answer, then Billy is in the answer because Kathy saw a Honda. Then she could not have seen a Mazda, and if she didn't see a Mazda, Jimmy can't be in the answer. So we can't allow Billy and Jimmy to be in the answer at the same time. This model actually allows that. Okay? And there's other things like that. So there has to be, the data in the answer has to be consistent with respect to what's picked in the base data. And so we cannot, it turns out, possibly represent the answer in our model. I'm just going to say quickly how we fixed it. We fixed it with something called lineage. And lineage sort of means where something came from. And in this context, what lineage meant is that we are going to store with each value in the answer pointers to where it came from. Billy came from Kathy, Honda, required 2 different alternatives. Okay? And that's what happened. And it turns out we proved a theorem that says if you have the data and you have the lineage, then you are correctly capturing the answer for every possible query result. And that was a pretty strong statement that we were able to make. But I'm now going to tell you about the magic moment related to this. The context of this work was a project that we called TRIO. And we called it TRIO because it was a system we built with 3 components: data, uncertainty, and lineage. And when we started the project, it was motivated entirely by the fact that there were applications that needed all 3 of those. Scientific data, the data was uncertain, and people wanted to keep track of where things came from. We also looked at entity resolution, another problem where we had uncertainty of lineage. We never in our wildest dreams imagined that lineage would turn out to be the key to representing uncertainty. We just didn't, that wasn't what we were thinking about, we were just motivated by applications. So then I'm wondering, how did that happen? Was it implicit that there was some connection between these things, and that's why we put them together? Some unconscious hunch? Maybe divine intervention, pure luck? I don't know, but I would consider that a magic moment, and the whole project came together in that way. And probably for me, sort of one of the most poignant moments in research, when everything fell into place. Okay, so summarizing research, I gave a recipe for a database research project, drop an assumption. You need to reconsider all aspects of data management and query processing. Approaching a new topic, I feel strongly about foundations first and then implementation, but there are other people who have built their careers on the other approach, and that's fine too. And lastly, I would just say don't skip on foundations, and I hope if I've convinced you of anything, I've convinced you that data models and query languages can actually be quite tricky to work with, surprisingly tricky, starting with the original days of SQL. Okay, and now I'm going to move to teaching. Should I take a few questions on the research, or should I just plow through the end? What the organizers like? Plow through. Okay, I got some plow through. Okay, switching gears completely now. Let's switch gears and go back to the fall of 2011. In the fall of 2011, the 3 standard computer science courses were offered to the world for free. It was AI class, and machine learning class, and database class. And they were not at the time when the term MOOC didn't exist, but it does now. They're known as massive open online classes. And it instantly launched, I would say, an online education frenzy that's going strong. Here's a question you might be tempted to ask, and I'm going to tell you not to ask it. I don't know where the online education frenzy is going. I think it's still anyone's guess. I'm not going to speculate on that. You can ask me very specific questions, but don't ask me where it's going in the long run. Remember when I said I'm not a visionary? Not a visionary. Okay, so let's go to fall 2011, and it's time for me to teach my Introduction to Databases class again. I teach it every fall. I had 150 students enrolled in my standard class, which is pretty typical. Actually, it's now up to about 300. But I also offered it to the world, together with 2 other courses at that time. We called it DD class, and I was stunned to get 60,000 students, quote, enrolled in the class. Now, enrolled just means sign up for an account, and that's very important to know. That enrollment number, I get upset when people talk about those. They don't really mean anything. Meaningful is that 26,000 people submitted at least 1 assignment for grading that fall. 6,500 completed the entire course, and that's a big 10-week, it's the equivalent to the standard course. 10% completion rate for a MOOC is considered quite good, actually. That's at the top end these days. Now, after the first offering, I offered 2 more synchronous offerings, and then now the materials are just out for people to use whenever they want. Rough estimate as of this fall, 500,000 people have gotten accounts, 8 million video views, 600,000 assignment submissions, and 25,000 statements of accomplishments, which is what we give out when somebody completes a course. Okay, magic question. Surprising number of you have come up already and told me you took the course. How many people out there have taken at least some portion of the course? Okay, so how many of you have taken some MOOC? So substantially more. You should do it. It's a great field. Absolutely. Not course offering where there's a start date, there's an end date, and there's assignments being due at a particular point in time. And the important thing is that all of these rely on the same basic set of course materials. So all of them rely on having videos, purpose-made videos, often with short quizzes inside the videos to keep people engaged. All of them are involved in having quizzes online. Many of them have automatically checked programming exercises and then various support materials. Whether you're doing a flipped classroom, whether you're putting your course material online, or you're doing a MOOC, that's the core material that has to be there. And in my case, I use that core material for all three. I did a flipped classroom, I put it online for self-study, and I did MOOCs, all based on exactly the same materials. Now, I want to tell you a little bit about what I did in my flipped classroom, because certainly if I'm giving this MOOC out to the world, and then people are paying a fortune to come to Stanford, or the parents are paying a fortune, they better be getting something more for their money, right? So what do they get for their money? What do they get in the classroom? We try to make the classroom worthwhile. So in addition to the online materials, we have professor-led problem solving. Actually, there's a lot of benefit for students to work on problems with the professor there, sort of going back and forth. So I developed a lot of materials where I would have a stage problem and people would work a little bit, then we talk about it, they'd work more, and so on. Also left time for more guest lectures, more research and advanced topics, and help sessions in the classroom time. We also had, in my class, we have written challenge problems, so problems that you couldn't do automatically online, had to be graded by hand, a programming project, and then thorough exams as opposed to multiple choice exams online. For the MOOC, we have the online materials, but you can't have anything in a MOOC that involves, one-on-one student interaction. It has to scale, by constant. So unless you start doing peer grading. So for the MOOC, we had multiple choice exams. We had a discussion forum where people could get online and talk about the class, and then at the end they got a statement of accomplishment. And the discussion forum, at least for my first MOOC, developed a big sense of community in the MOOC, and I'm going to talk a little bit more about that in a moment. And I think that was very important. So now I'm going to make a statement that when I did that first MOOC in the fall of 2011, that was one of the most invigorating teaching experiences of my career, doing that. And some of you apparently were involved in that experience. And I'm going to even go one step farther and say it's one of the most invigorating experiences of my career, period. Just that 3-month period, doing that class, the excitement around MOOCs, the effort I put into it, and that was surely a magic moment. I'm just going to show you a little bit of the course materials and what it looks like. Some of you are very familiar with this. I was not very high-tech when I put my course online. I had a little windowless room with a webcam, and I had a little tablet that I wrote on, and I had a teaching assistant who helped with some of the editing. Very, very low cost, low tech. This is a picture of a sample of one of the lecture videos. You can see I had a PowerPoint slide, and then you can see my picture in the corner, and as I was recording, I would write out the slide using the tablet. That was it. For the database class, I wanted to do a lot of demos, because a lot of database got queries and answers and so on. So here's an example where I'm doing a demo. I've got a database down here and a query up here, and I'm talking about it down in the corner. Again, many of you are familiar with this. In the middle of the videos, these quizzes would pop up. So this quiz popped up and asked a question about the content. Students could skip, or they could try to get the answer, not forcing them to do it. Then an explanation of the quiz would come back. So it seems that studies have shown that students do much, much better if periodically a quiz pops up and engages them. We also used a quizzing system that was actually developed by one of my colleagues many, many years before the MOOC movement, which is a quizzing system where we have for every question in the quiz, you develop your quiz so that every question has it's a bunch of right answers and a bunch of wrong answers, and they're all sitting there in a database. And when the student asks for the quiz, they get an instantiation that'll show the question and will randomly pick a right answer and a set of wrong answers. And that gives the students the illusion that every time they run a quiz, they're actually getting a different quiz. And the students love that. And both on my on-campus class and in the MOOC, we allow students to do quizzes over and over until they get a perfect score, because each time they do the quiz, they're actually getting a different instance of the quiz. So they can't just figure out guess the answer over and over. And it's very XML, constraints, views. So pretty sophisticated problem sets where the students would get the database, be asked a question, submit a query, and have to, again, they could do it over and over until they got it right. And the students loved that too. And we used the same ones for the standard students as the online students, and they just got progressively harder, and the hardest ones were actually quite harder. Then, as I said, I really enjoyed it. I really threw myself into the experience. It's really what I did for that 3 months. For a personal touch, every week I made a video where I talked to the students. It was about a 5-minute video, and we called it a screen-side chat. And I think only Americans of a certain age would know why we called it that. There was a president, Roosevelt, yes, it was Roosevelt, who every week went on the radio and talked to the American public about what was going on, and he called them fireside chats. So we called the screen-side chat every week. I came on chat with the student. We even had a picture of a fire there, basically like a fireside chat. Like, again, not too many people made that connection unless they went to an American school and learned history. The American Thanksgiving holiday, we put up a turkey. That's what people eat at Thanksgiving in the U.S. And then at winter time, we had the snow going. And what I did in these chats was try to cheerlead a little bit. I could look at the discussion forum and I could see what people were struggling with. Sometimes I would talk about what parts could be skipped and what parts were important and so on. And it just added, I think, a personal touch to it. So why was this so fun for me? Well, it was mostly, I think, because the students, the public students, these thousands and thousands of students were extremely appreciative. Much more appreciative than the Stanford students, I have to say. You're not going to be able to read these here, but these were things people put on the discussion forum. Here they're talking about who they are, 75-year-old, 12-year-old, person who's been out of work and was trying to get a job, and then emailed me later that they got one. Many people emailed me that they got jobs based on what they learned. Here, people talking about how much they love the course, how it's a gift. They called me a rock star. I've never been called a rock star. And then someone wrote a poem about the course. They were so happy. The students that came rushing in from near, far, and near, everywhere to gaze upon this wondrous thing, a precious gift for all of us to share. And it goes on and on and on. So it's pretty rewarding. And one of the very rewarding things was out of that whole mass of 60,000 accounts, a top student emerged. Clearly a top student emerged. This student posted 900 answers on the discussion forum. There was no discrimination against dumb questions. So if it was a really obvious question, the person answered nicely, patiently. Every answer was correct. It was of the perfect length. It would include examples in perfect English. This was definitely a magic moment to see this student emerge. I didn't know anything about the student except her name. It was a woman. And other people liked that student too. Amy was her name. So there was a lot of speculation on the discussion forum about who that student was, and people started to decide it was me masquerading as a student. And then this person proposed marriage to the student. And proposed marriage using XML, actually. It says the XML tag down on knees, and then goes on to propose marriage. So actually when the course was over, and I waited until the course was over, I looked up the student and I contacted the student. It was a woman who was living in San Diego. She had graduated from college and was working a boring job and was doing this to educate herself. I flew her to Stanford. I offered her admission to our master's program as a teaching assistantship, and she didn't take it. So she was tied to her family's company. But anyway, it was quite a poignant experience for sure. Were there any downsides to this experience? I'm acting like it was all fabulous. There were the complainers. It's surprising to me that this course that we worked so hard on can be given to everybody for free, and they complain, but people didn't. There was some complaining, people would complain about the formatting of the quizzes, or we waited 10 seconds for something, we should have waited 20. I couldn't believe that people complained. And then at the very end, there was this big uproar on the discussion forum, because at the very end, everybody got this statement of accomplishment, and it said, this user account completed the course with the following score. And people, it was a PDF file, and people were somehow expecting much more than that, some people. And they got very upset, and they started flaming on the discussion forum. And then there were other people who came on and said, how can you possibly be complaining say Stanford on it. And then someone else said, yes, it says Stanford all over it. It says, this is not a Stanford course. You are not a Stanford student. You did not get Stanford credit. And then other people pointed out, you just edit the PDF. Anyway, there were complainers. That was kind of the downside. And it's important to put those out. Unfortunately, well, I'll come back to that in a moment. There were also cheaters. Absolutely cheaters. How do we know there were cheaters? There were people who took the midterm and final exam and got a 100% perfect score in 90 seconds. How did they do that? They got two accounts. They got one account, they took the exam, they wrote down all the questions, they went off for a day or two, figured out all the answers, and then went to their second account and did it in 90 seconds. So we knew there were cheaters. We didn't really care, but for, when you're actually doing credit-bearing online courses, that's a big deal that has to be dealt with somehow. And then the second and third time I did the move, I say there was a bit of a letdown. There were more complainers, people, there were a lot more moves, it was a lot less special. It was very special doing it in the first time it was being done. Just wanted to mention the current status and advertise out there. What I actually decided to do after 3 MOOCs and 3 doing a massive course is to divide all the material into mini courses. And I think this makes complete sense. It really doesn't make sense if you're delivering to people to say, okay, you have to do everything. Why not pick and choose the things you care about? Maybe you care about SQL, maybe you care about semi-structured data. Maybe you're a database expert, but you don't know how to do recursive SQL queries or something like that. So now we have 14 mini courses, and there's various pathways through them. So they're based on topics, and then you can do the basic pathway, where it's just the basic stuff, or extended, or you can do comprehensive, where it gets all the way to those very difficult problems I mentioned. It's self-study, so there's no start and there's no schedule. The plus of that is that it's always available. You can start at any time. The minus is you don't get one of those top students there helping the whole class out. I still get a steady stream of thank yous. I got many already this morning. When I first did it, I got chocolates in the mail and people coming to my door saying I had changed their life. It's really extremely gratifying. Again, one of the most gratifying things I've done in the Magic Moment. Thank you. So questions on anything, you can wind way back to that lineage if you want. Yes?
So, there's been a lot of flux of NoSQL,
Yeah.
all that schemaless.
Right.
So there's a huge debate about what 40 years of database fine-tuning, all the perfections that have been achieved in the relational world.
Right.
Are they of no use in this new web properties?
Right. So the question is about NoSQL or NoSQL. So it started with Hadoop. Really, I think was the sort of beginning of NoSQL. So it is definitely not the end of traditional relational databases. You're going to see big companies that have money to spend are still going to be investing their money in traditional, big, very reliable, easy to use, scalable traditional databases. What the NoSQL tends to be used for is people who want to get something up fast. They're not going to get the same properties. They're not going to get transactional properties necessarily. It also doesn't scale as well as they would like to claim that it scales, but it is often open source and it can get going fast. And so for a certain type of simple problem, it absolutely has a place. So I agree that neither one is going to go away. My guess is that NoSQL will get more and more reliable, and then it'll probably start costing money, and then we'll have a problem. But yeah. I do not consider it it's a change, but not a huge disruption. It isn't going to put the old way of doing things out of business. Other questions? No other questions? Oh, we got one, two, one there, one there.
You talk.
You can say it and I can repeat it.
So you talked about lineage, which was
Yep.
Eventually became probabilistic databases and stuff. The data science world hasn't really embraced it, and I'm on a number of committees and chairs and stuff. But when you say data science conference, except Sigmod say, but the machine learning people are sort of dominating that.
Right.
And the databases very rarely squeezes things, even in things like uncertain databases, missing values, generating features automatically.
Right.
Should it be part of the same community? Or?
Yeah, so this is a great question. This is the question of the database community and the machine learning community. And those communities have historically been quite separate. And maybe machine learning is trying to grab data science. I'm not sure. I don't know. Databases have been about simplicity and scalability. And machine learning historically has been about learning models, complexity, and not about scalability. And I think the best work that's going on right now, there's some very good work by one of my young colleagues at Stanford, for example, is in putting those two worlds together. In making machine learning scalable through use of database technology. And it will come. But they have been historically very separate. Yep. And you know, one of the things I guess I don't have to do it separately, but machine learning is also often about batch processing, not so much online processing. And that's one of the fundamental differences. But that doesn't mean that the two worlds shouldn't get together. They should get together, and they would. Yeah. There was a question here. Yeah. You can shout. I can try.
Your model of research is just getting through the concept and ideas before you start implementing it.
I'm not going to understand what you say. I think the microphone is muddling your voice.
Why don't you just go ahead and
Go without the microphone and then
So
yes.
your idea of research where you say going through the concept and idea when
Yeah.
before you start implementing this.
Right.
So how much would you suggest? So I think there's a trade-off between the two. And given a PhD student and the more people like me here, so how much pre-planning and how much of implementation, what would be the trade-off for us?
Right. Yeah. So the question was, you know, I said foundation, then implementation, cut and dry. If you're someone like a PhD student, you don't have that much time. You know, how do you balance the two? So first of all, I'll say it's not nearly as black and white or simple as I made it. I sort of act like, okay, you spend this time on foundations, you're absolutely done, then you implement. The truth is that when you implement, usually you found something might be wrong with your foundations, you have to go back. And sometimes when you implement something and put an application on it, that's when you decide you actually solved the wrong problem and you have to go all the way back again. So in fact, I have a slide which I didn't include that shows that there's much more of a feedback loop between the foundations and the implementation. But I would say if you're a PhD student, your advisor ought to be kind of managing that trade-off. I think as a PhD student, it is important to get to the implementation phase. And so, you know, don't implement willy-nilly and have no clue what you're doing and just sort of do stuff randomly. But I do think at some point you do have to move on. So I exaggerated a little bit for effect. I do, at some point you have to just say, okay, this is it. I figured out roughly what I want to do. I'm going to go for it and start coding. And that's fine. Yeah. Other questions?
I'll ask.
Yep.
So, in a country like India, where there's a lot of stress on people being certified, they get a record from a university that
Right.
there is an examination they passed, there is a certificate they can take of having even attended this conference or having attended a talk or having finished a course. How does all this move around?
Right, yeah. So the question was, in a country like India, where there's an emphasis on formal certification, what happens with MOOCs? So when we were looking at it in 2011, we refused to get into the certification. We just said, we're not going to go down that road, it's too difficult with the cheating and so on. And my personal philosophy was that learn the material, they can use that in interviews. You don't know, what does it matter whether you have a certificate, you go in the interview and prove that you know that. But I know that's not the reality. And the reality is in a lot of places you do need a certificate. And for better or worse, there's been several companies that have launched on the basis of this movement. And one of the things that they're doing is certification, but you pay for it. So that's where it's going. And that means you pay to have, there's various ways of certifying that it's you, but in the end, typically you have to go in person to a testing center, take a final exam, show an ID, you're paid to have that privilege, and then you get the certificate. And I don't think it will ever get to the point where there will be a way to do the courses for free and to certify. That seems unlikely. Although I think Udacity might have a few courses where you can do that, but that's probably stuck you in, so you start taking the paid ones. I mean, so the money has to come from somewhere at some point, and the certification does end up costing, right? Sometimes it's talked about using biometrics, face recognition, all kinds of ways of assuring that as a person who did the course, right? But that's one direction it is going, because people do want certification. But I would also argue, I got a lot of people who said that they got a job or a promotion or a better assignment just based on the knowledge they learned from the class and proving they had that knowledge without having any formal certification. Yeah.
So it seems like when you first started, it seems like a lot of effort from your side. You were passionate about it, so you sort of spent time on it. How do you make this sort of a larger movement with minimal effort? So I'm thinking more if you go into elementary, high school in remote areas in India.
Right.
To get the quality teachers, it's not always possible. Is there a model that you can work which would be fairly low on logistics?
Right.
To be able to get this across?
Well, so the point was that I put a huge amount of effort into the course, and I did put a huge amount of effort into it. But of course, now that everybody can take the course, right? So my effort is scaling out. I think in a place like India, or actually anywhere in K-12, I think a lot of the material is common enough that you don't need each sort of unit to do their own. So there's the Khan Academy. How many people look at Khan Academy videos? So these are mostly for K-12, but those are videos that anybody can use anywhere. And so I think it does scale, but not with each individual unit making their own course. Is that not quite your question?
Somewhat, yeah. One thing, I mean, it seems like you need a very passionate person to be able to, if I were offering a certain course, maybe even like, 8th grade physics, unless I was motivated enough to do it, I'm trying to see if there is a model where maybe Stanford have a way to make it simpler for professors to be able to.
Oh, yeah, okay. So I do think, I don't have a concrete answer, but I think that Coursera is developing suites of tools to help people. You can only help them so much. Eventually they have to do the content. But I think that there is some of that going on. Somebody's nodding. I'm not 100% sure, but I'm pretty sure. I have kind of ignored it because I already did mine. But yeah. But again, eventually they're in a business, and I'm not sure what the business model is necessarily for making those. There's a difference for Khan Academy, for example, is non-profit, and so they don't need a business model all the time for what they do. So they could, for example, make tools. Coursera is a profit company, and they need a business model. But yeah, it's a good point because it's a big effort. But on the other hand, for my course, I think the big effort is more in content than actual production. Yeah. Other questions? Yeah.
If classroom approach that you tried,
Yeah.
are there any downsides? I mean, there are often speculations that people don't actually, the students don't actually view the video, so
Right.
figure out some downsides.
It's a great question. Does the flipped classroom have downsides? Absolutely. I'm not even sure I believe it myself. So we can talk about this a lot. But there are downsides to the flipped classroom. Students do get tempted to put off watching the core material, so they'll watch it all the night before the exam. That's one of the downsides. But students also, at Stanford, all of a sudden there was a flurry of faculty trying to flip classrooms. actually said, well, my life is so hectic, the lectures are soothing. And then another effect has been that some faculty are tempted to put more material in if it's flipped. So they say, okay, all the core material you and I know, I'm trying to add it, all that's more stuff. Students don't like that either. And sometimes what goes on in the classroom is a little disorganized because faculty are used to lecturing. So I would say the flipped classroom may or may not survive as a concept. There is this notion of the blended classroom, which is like half flipped. Sometimes you do lectures, sometimes you don't. Maybe that's where it'll end up. But yeah, it's a great question. Yeah. Other questions? Yeah. Yep.
You answered the classroom one where you go over the details after the video and you explain the main concept in the classroom.
Yeah, so that might be what's a blended kind of thing. So yeah, so details in the video are main concept in the classroom, or you can even do the other. You can do the main concepts in the video and the details in the classroom. Yeah, and that might also be thought of as a blended classroom. So I do think this is all going to work itself out maybe into something that works well, but I don't think it's going to be a whole bunch of flipped classrooms. And it probably won't be all traditional lectures either. It's yet to be determined where it falls out.
One last question. I think you mentioned Michael Stonebreaker a couple of times, and over the past 2 years, he's written a lot of scathing stuff about much of the big data databases.
Right.
What's your view on that?
So the question is, what's my view of Michael Stonebreaker's scathing writings about certain aspects of databases?
Big data.
Yes. So he has always been a controversial figure. He's done amazing things, but he doesn't usually welcome things that are of a different area that he's chosen to go. How's that? So he's sort of, I mean, I like the guy basically. I really do. He's done amazing things, but he's often almost purposely controversial. It's kind of a personality trait. Yep. But I'm not going to weigh in on my opinion. I mean, there's the stuff he does, which is great. There's the stuff he criticizes, which I think is also great. Anything else? Okay. Thank you.
So in this session, we have another invited talk by Professor Anuj Dawar. Professor Dawar is Professor of Logic and Algorithms in the Computer Laboratory at University of Cambridge. He is also a Fellow of the Robinson College. He serves as President of the European Association for Computer Science Logic. He has been part of the University of Cambridge for 16 years in a number of capacities, including university lecturer, reader, and professor. His interests include applications of logic in computer science, especially in those areas of theoretical computer science where logical and combinatorial methods combine in the study of algorithms. So this includes several areas like finite model theory and its connection to the study of computational complexity, theory of databases, complexity of games, explicit power of logical formalisms, and so on. So please join me in welcoming Professor Dawar to his talk.
Just waiting for the projector to come back on.
Well, let me begin by saying a big thank you to the organizers of this event for inviting me here and giving me the opportunity to come and speak to you. Now, I'm a theoretical computer scientist, as you heard from So please kind introduction. And I'm just sort of engaged in a project which I'm starting off on the study of symmetry in computation. Now, this is sort of an initial stage of the project. Looking ahead, what I want to do in this talk is tell you a little bit about the motivations for this kind of study. And my title is sort of abstraction, symmetry, and complexity. I want to relate these ideas of symmetry to things which pop up in theoretical computer science all over the place. Right? That is the ideas of abstraction, symmetry, abstraction and complexity, and tell you a little bit about why I think they're important. Okay. So, it's been said that computer science is the science of abstraction. Abstraction is so central to the subject. In A. Nolan's textbook on the foundations of computer science, they call it the mechanization of abstraction. Computer science is the mechanization of abstraction. What does this mean? It actually means very different things. One traditional view, which is not going to be the main focus, what I talk about abstraction, is the sense in which computers are machines which are built by and designed through layers of abstraction. This is simply because there are incredibly complex machines, and the only way we can get our heads around the complexity involved in the design of a computer is by designing in layers of abstraction where we hide the complexity of the lower layers by building layers on top of it which are configurable programmable layers. Okay? This is sort of a typical picture you will see describing layers of abstraction with hardware at the bottom, say application software at the top, and various layers, each of which hides the details of what's going on below and presents a view to the next layer above of a configurable machine. That's one important sense of abstraction. And sort of maybe a little philosophical point right on the side. It's precisely these layers of abstractions that make computations useful in a sense, because computers, unlike other machines, are useful precisely because they are about something else. They represent meanings, right? And meaning that they're in reference to other things out in the world, unlike, let's say, a car, which its function is just to move. The purpose of computation is to represent other things, and it is precisely, if it wasn't for these sorts of abstractions, the only thing computers would be about would be electronic circuits. Okay? But besides from that point, there's another sense, an important sense in these computations of abstraction. Now, I find this very often. When, with some students, one of the hardest things to get going with, say, programming is to learn the art of abstraction. That is, you have a real-world problem you're trying to solve. In order to turn it into a computational problem which you can use a computer to solve, what you have to do is forget a lot about the details of the real world. That formulated as an abstract problem. I mean, I have students working with design railway timetables with a straight programming system. Now, we actually start with the real world of trains, tracks, stations, etc. There's an enormous amount of detail there which you don't want to represent in your system. And so the important first step is to identify what is the problem you're trying to solve. And that is a step of abstraction. Abstract away to the real world, right? In the sense of A.O. Nolan's foundation textbook, this is formulating a data model. What you represent and what you don't represent from concrete messy reality, which is always full of messy detail, which you don't want to represent. Now that's the sense of abstraction that I want to pick on. Okay? And say a little bit more. So, I talked about railway timetables. I'm going to take another kind of problem you might want to solve. Let's say you have a college. You have a bunch of new students coming to your college, and you have to assign them to hospitals. Okay? So there are a bunch of new students, there's a bunch of hospitals, you want to put these individual students into hospitals. First of all, of course, you have to make sure there's enough rooms. So let's say the number of rooms and the number of students matches up. But then there is a number of constraints, right? Some maybe you have students with disabilities, there are only certain rooms they can use. They may have other constraints they may even have preferences, etc., etc. Once formulate all of these constraints, preferences, you want to find an assignment which satisfies that. You've got yourself a data model. Your data may contain lots of other irrelevant details. Irrelevant to the student match problem, like the student's date of birth or other things. And so, what gets included in your data model and what doesn't is an important step to abstract. I mentioned this problem partly because I look at what looks like a completely different problem, but once you take the step of abstraction, it's very similar. This is one that was suggested to me by a colleague in England. I suggest to somebody who worked on it. So this is now, a matter of life and death. In the National Health Service in England, they run a kidney donor program where people who need kidney transplants are put on a register for kidney transplantation. Typically what happens is, if you need a kidney transplant, because you can get a transplant from a living donor, you also get a family member willing to donate a kidney, and if the tissue samples are compatible, it's a straightforward thing. You have a donor, you have a recipient, and you carry out the surgery. Sadly, it doesn't always work out that way. You have a donor, you have a patient, but they turn out to be incompatible. So what do? Well, the next best thing is you find, the next best thing is you find another pair of an incompatible donor and recipient, where it so happens that donor 1 is compatible with recipient 2, and donor 2 is compatible with recipient 1, and you arrange a kidney swap. Okay? So you have 2 kidneys donated, 2 recipients, and you carry out an exchange. This is now logistically a bit more complicated in the sense that you have to carry out 4 surgeries simultaneously. But this sort of situation arises. But now that you have a register of willing donors and patients, you can actually do something even more ambitious. Okay? Because likelihood of finding 2 pairs which happen to be crosswise compatible as in this picture is fairly low. What you'll often find is a chain of donors and recipients with compatible matches, and what you now have is an algorithm that runs on your database of donors and recipients and picks out these matches. The algorithm is not that difficult to implement. Right, so algorithmically this is not that challenging a problem, of course. The real challenge here is the logistics involved in carrying out a whole number of surgeries simultaneously, but they do this, right? They pick out up to, say, half a dozen or maybe even 10 different pairs, and then simultaneously in several hospitals, the patients go in, these kidneys are flown from one to the other on helicopters and so on. So this is actually implemented in practice, okay? So, why am I telling you all this? Well, the thing is, what I wanted to get at is that the algorithmic problem that we're solving over here is essentially the same as the matching the students to the rooms. There's at the heart of it, there's a very similar problem. And to formulate a similar problem, you have to forget about the fact that it has to do with kidneys, or students, or rooms, etc. and formulated at an abstract level. That's the level of abstraction I'm aiming for. And this is one which, for people who have done graph algorithms course, is a very familiar one. It's a bipartite partnership problem. Okay? If you haven't done it, it doesn't really matter. So the point is that the graph is a data structure which captures exactly the relationship we want to represent here. Namely, we have these entities, whether they're students or groups or patients or kidneys. We have these entities and we have relationships between them. And that is the level of abstraction we want to capture in our data, usually represented as a picture like this. Bipartite just means we have collection of entities on one side and a collection of entities on the other side, and the relations all go across from each other. So that's what a bipartite graph is, and we're looking for a matching means we're looking for some collection of edges in this which describe a perfect matching between these two. Now, in this particular graph, I'm trying to see. Yes. There is a perfect matching. It matches this one to this one, that one to that one over there, and this one to this one, and that one to that one. And you can match all four. You can match those four with those four using just the relationship in between. Okay? So this is the graph matching problem. The point is, think about it at this abstract level, rather than at the concrete level of the two examples I gave you. Allows you to reuse the algorithm in ideas involved in, say, the student group and group problem in the context of the kidney assignment problem. Right? And I don't just mean it allows you to reuse code that you've implemented, that may well be true as well, but more that the fundamental level, this is a level at which people often think of designing new algorithms. They think of it in terms of graphs and abstract objects like this. And those new innovative algorithmic ideas then may end up being used in a variety of practical situations. So that's this, what I call computational abstraction, which is different from my picture of layers of abstraction on my first slide. It's the kind of abstraction I'm talking about. Okay. I said I'm very confused. So abstraction is what I deal with. And I thought I'd share with you a little joke from one of my PhD students who once, when he was working on a paper, sent me a draft. I changed the title, but the abstract began. I don't know if you can read this. This might be useful. I'm a theoretician. Of course, it's abstract. If you want concrete, go to a building supplies cartoon. So abstraction is what we theoreticians do. Okay. But when I talk about theoreticians, okay, theoretical computer science also comes in many different varieties. And there is a common division among theoreticians. They talk of theory A versus theory B. Okay, so this probably terminology you're not very familiar with. I know some of you are very familiar with. It's sort of inside terminology among theoretical computer science. The terminology comes from the fact that well, maybe let me tell you a little bit about fundamental divisions and tell you where the names come from. The fundamental division is this. So, theoretical computer scientists have been more concerned with essentially two fundamental problems in the field of computer science. One is the problem of how do you ensure that programs are correct. And the other one is how do you ensure that programs are efficient. Okay? Correctness and efficiency are the two cornerstones of the field, and they have very different sort of methods are used, if you will, mathematical methods in the two in field concerned with correctness, verification, etc., as opposed to in the study of algorithmic efficiency, study of resources, and so on. They're very different mathematical fields, the tools used are very different in mathematical culture, so these are actually very distinct research communities. We don't interact that much with each other. They still fall within the general rubric of theoretical computer science. And back in about 1990, there's a famous book published collecting called The Handbook of Theoretical Computer Science. It had volume A and a volume B. And volume A was algorithms and complexity, and volume B was semantics and verification. Also, there's a journal, the Journal of Theoretical Computer Science. It's not an ACM journal, so perhaps I shouldn't be mentioning it here. It also publishes in two parallel streams called volume A and volume B, and it defines the scope of the two streams. Well, I mean, this is taken from their website. Theory A, algorithms, contrast, complexity, and games. Theory B, logic, semantics, and the theory of programming. Okay. So these are two different streams of theoretical computer science. What do they have to do with my story about abstraction? Well, in a sense, part of what I want to get at is theory B is very much concerned with the problems of abstraction. Theory A has been very little concerned with the problems of abstraction in a sense. And I think this is part of the reason for the mismatch between them, and that's what I want to tell you a little bit about. Okay. So, one of the original abstractions of computer science is to abstract the idea of an algorithm. Now, the idea of an algorithm is an ancient idea. The idea of sort of a calculation done by mechanically following certain rules is an old idea. And people have been asking for a long time before, what can you do algorithmically, and what can't you do? That's the question. And Alan Turing, in the 1930s, gave a formal mathematical definition of what you can, of what an algorithm is. That is a Turing machine. Okay? So usually we picture a Turing machine as some sort of picture like this. A Turing machine is some device following some rules given by the state transition table. There's some set of rules. Looking at a tape which is a string of symbols. And the point is at any given point in time, you just look at one symbol, make some little change, and carry on. So it captures the idea of a program at a very low level. Okay? Note, in a sense, very low level of abstraction. We're talking about manipulating single bits and a finite transition table. Okay? The point is that sort of work on various forms of computation leads people to formulate the church theory thesis, which says essentially that all models of computation are pretty much equivalent to this one, in the sense that they can do the same thing. Whatever you can do in one model, you can do in another. Okay? So why would you model with any of this? You've got a universal model that does everything you could possibly want to do computationally. So for the purpose of more computation, are we done? Well, in some sense, the whole development of a strand of high-level programming languages shows you that that's not right. Right? There is a huge variety of computational models out there. Any programming language is a computational model. Why do we need them all? The point is that what they do is give you different abstractions. Okay? I stress the point that the Turing machine works at a very low level of abstraction. We want things, when we actually program, we want high levels of abstraction. We want, to be able to think of objects and messages and all these other sorts of things, because that's the level at which we're formulating the problems we're trying to solve, the level at which we're formulating the programs we're solving them, and so on and so forth. Okay? So, this great variety of computation models is all about different kinds of abstraction. And theory B research on semantics, programming languages, and so on, is all about the formal semantic properties of different kinds of abstraction. Right? That's really what it is. precisely in their simplicity, it's a very simple model. It gives you almost no useful programming abstraction. Its usefulness is in proving impossibilities. Because of its simplicity, you can actually prove that certain things are impossible to do with a Turing machine. And then, by the fact that all these computation models are equivalent, you know that they're impossible to do in any of these richer languages, and so on. Okay? So the value of Turing machines comes from impossibilities. That's why we like Turing machines. And that sort of thing, concerned with impossibilities, is an important strand of research in theory A. That's the work of computational complexity, for example. Computational complexity, as I said, realism, the efficiency of programs, how efficiently does a program run to solve a particular problem. But just as often, we want to prove that some problems don't admit any efficiencies at all. Okay? That's an impossibility result, and for that sort of impossibility result, what we call complexity lower bounds, a simple model like a Turing machine is very useful. Okay? So that's why studying how to do complexity is often formulated in terms of low-level machines such as Turing machines. You pick up a textbook on complexity, on computational complexity theory, it will begin with something like a Turing machine, and it will define the complexity of problems, running time of programs, complexity tasks, all of this in terms of this kind of. So you use the simple model to prove impossibility results, but the results are robust, as I said, in the sense that they do prove that because these machines can simulate higher levels of abstraction, and the simulation itself is reasonably efficient, that means that if you prove impossibility results at the low level, they're pretty much small. Okay? So, I'm not going to bother with the details. The point is that if you're interested in rather broad brush classification of complexity, it's enough to look at these rather low levels of abstraction. Okay? But, and this is the point I want to make, the description of complexity in low level terms violates the principle of abstraction, which is what I'm contending is an important central principle in computer science and all computer science. It's all about abstraction. Okay, so how did this arise? Now, in the field of computational complexity, maybe most famous of the problem is the problem of whether P is equal to N. Right? This is, possibly one of the most famous problems in computer science as a whole. Since 2000, it's a problem with a prize on its head because the Big Mathematics Institute offers $1 million prize for resolving the problem one way or the other. What's the problem? We essentially have two different types of problems. P is the set of those problems that can be solved efficiently by an algorithm. Now, that's not formalization, but formalization efficiently means that which is far out of the here, but let's not worry about that. It is a formalization of the notion of things that can be efficiently solved. And NP is those problems where we have an algorithm which, given an input along with a solution, can efficiently check that the solution is in fact a valid solution. Okay? That's how we can. We expect that not everything that is an entity is in P. That just being able to efficiently check the solution doesn't guarantee you can efficiently find the solution. Right? So there should be problems in here which are not in here. But no one's ever been able to prove that. And a proof is essentially what I would call an algorithmic lower. Right? If you have a proof, you have to pick a problem in here and show an impossibility result that no efficient algorithm could possibly solve. That kind of impossibility result, that's what complexity theories are always trying to do. That's what, that's in terms of the subject chapter, a real solid algorithmic lower bound that. But certainly in this case, it's not in. It remains open. And it looks like a big challenge. No one really has any clue as to how to go about solving it. Okay. Let me go back to the graph matching. Okay, remember, graph matching was an abstract formulation which covered the two examples I started with, the kidney donor matching and group matching. This is slightly more general, that I'm not assuming the graph is divided into two parts. So a graph now is just some set of vertices and some relation between them, and a matching is finding for each vertex exactly one paired vertex. So dividing the set of vertices into pairs so that the vertices in the pair are actually connected by sign. That's what a matching is. The question is, can we find one? Formulated this way, it's easy to see that the problem is in NP, because if I give you the graph and I give you the matching, checking that it's a matching is an easy problem. Okay? But in this particular case, it turns out it is indeed, but it's not obvious. It takes some work to come up with an algorithm which actually runs efficiently and find the matching. So this was already done by Jack Edmonds back in 1965, famous result. And the fastest known algorithms, I think, possibly as a part of the process, is due to Sidney Kali and Vijay, also dates back to about 1980. Okay. Now, I want to pick on this one result from the field of complexity to illustrate this point. Okay? We also find algorithms by operations on some abstract data such as graphs. So the graph is an abstraction of the things we are interested in, like kidney. And then we think about how to find the match in a graph, and we describe an algorithm through operations on graphs. I'll give you a slightly more concrete description of matching algorithm in a moment. On the other hand, when we talk about the complexity of algorithms, right, and particularly complexity classes such as PNNP, we define them in terms of Turing machines which work on strings of symbols, not on graphs. And this is a mismatch. Okay? This is a mismatch in levels of abstraction that I was talking about. Is it important? It's usually considered harmless because we know that any data structure, any rich data structures and graphs can be encoded as strings. These are just layers of abstraction, and they sit one on top of the other, and everything goes on at the level of bits, which are just strings of zeros and ones anyway. But it's important to note that this mismatch breaks abstraction. Okay? So, it may be, or in the case of that matching algorithm, it is the case that you only get those efficient algorithms, those two that I mentioned, by breaking through this level of abstraction and dealing with these underlying string representations. Those algorithms don't work at the level of at the abstract level that the problem is formulated. Okay? So, I mean, this is maybe a bit technical. So, understanding this is not crucial to the rest of what I'm going to say. But, for example, bipolar graph matching problem, where you had two sets A and B, you want to match every element of A to an element of B using the set of X and B. And algorithm starts with empty matching, nothing is matched to anything else. You choose an element of A that is currently unmatched, and you find what's called an augmented path. Okay? It just means you pick something with which it could be matched. If that thing currently unmatched. You're done, you found something you can add to the matching. If that's matched, you take the thing it's matched to, and then you carry on. And this thing is called an augmenting path. As long as it ends with something that's unmatched, you can change the matching to increase it to something bigger, and this thing is guaranteed to converge to an optimal matching. Now, that's the way the algorithm is described. It seems to be described, as I said, at the level of graphs, at a high level of abstraction. It's not talking about something simple. Except, there is this operation here, choose an element A, which doesn't really work. Because in a typical implementation, what will happen is, after you choose an A, you'll choose maybe, I don't know, if this is a list of names of your students, for instance, you might pick the alphabetically first one. And then you're using some property of the data which is supposed to be hidden by the abstraction. A choice of an arbitrary element almost always relies on concrete data which is supposed to be hidden by the abstraction. The way this is formulated precisely is that abstract data has symmetries. And if the program is written at the level of abstraction, then it should respect those symmetries. In other words, let me explain a little bit what symmetry means. We expect the algorithm to work at the level of abstraction graphs, it must respect symmetries as well. What does this mean? It means if you have nodes and graphs which are indistinguishable by graph properties, as there is really nothing about the graph that makes them look different. In other words, say in your graph you have two students, in your student room matching problem, you have two students which have exactly the same constraints and preferences, then your algorithm should not treat them differently if it respects the level of abstraction. Right? Choosing one or the other based on the alphabetical order of the names would be breaking the level of abstraction. Okay, so that's what I mean. Symmetry of the graph and why something that works at the abstract level needs to respect symmetry. So the question is, what algorithms have this property of respecting symmetry? And you can show, as I said, that the fast algorithms for graph matching that I mentioned before, for example, the value of 0 algorithm, don't. They are not symmetry preserving in this sense. Can you solve matching simultaneously at the level of abstraction which is formulated as a preserving algorithm and efficient? Okay. I just want to raise this question. I'll tell you the answer before the end of the talk. So, but maybe we can ask a more general question, no longer specifically about matching. Take any problem which admits some efficient solution. Is there a way of solving it efficiently while doing it at the level of abstraction which the problem is formulated? So this is roughly the following question. Is it possible to design a language with high level abstractions, for example, for graph structure data, in which every problem that admits an efficient solution can be expressed in the language in a way that can be automatically compiled to an efficient program? Okay? So you want the language to be at the level of abstraction of the data, but you want to compile it out to an efficient solution. Right? And this is sort of you can turn this into a well-formulated theoretical question, a version of which was essentially raised already back in 1982 in the context of database theory by Ashok Chandra and David Harrell. And that question has essentially remained open essentially ever since, right? More than 30 years, it still remains an open question. So, what would a solution possibly look like? We want a formal model algorithm that works in abstract structures like graphs rather than printed symbols. And these things have been well studied in the context of database theory languages, right? For a while, talked about being declarative means that they should be written as an abstraction of the data rather than relying on the, hidden representations of it. So you can define a formal model like a machine, where now the data is not a string of symbols, but it's given, let's say, by tables, like graphs, and let's say like a relational database. And we have an internal store, which consists of some fixed number of registers, we can store numbers, let's say, and relations. And we can do operations like relational operations. Joins, sections, complements, possibly counting elements, right? So you can get a numerical value out, and so on and so forth. Now, this is a computation model which again you can simulate by Turing machine. And you can define the things. The problems are solvable if they efficiently of this model. I call it FPC. Never mind why it's called FPC, because it's a technical term. And you can show that most things which are obviously, that is, most problems for which there's an obvious efficient algorithm solving it, you can turn it into one which will work in this level of abstraction. And, that things, I'm not including them all. I mean, that's, for instance, counting the number of, if you're talking about graph structure data, counting the number of nodes in your graph would certainly be an obviously polynomial kind of thing. Computing matching, I don't consider to be obviously polynomial kind. It requires something original to prove that it is. But turns out many non-trivial ones are also accessible, but it is known. This is a rather technical result. But it's known that there are things which do admit efficient solutions, but not in this model. Okay? This is, as I said, it's known since it was cited in 1992, and I'm not going to tell you what the particular graph problem they define is, but I will call it the CFI problem. So you can define a more powerful model called abstract state machines, which allow for richer data structures and test relations. Again, never mind the technical details. The idea is that you can construct more complex objects by nesting step formulation operations. And they define this class of problem solvable efficiently on these abstract state machines. Take on trusted polynomial time. And now, it's an open question whether anything that's efficiently solvable is doable in this model. Okay? The thing that shows that there are efficiently solvable things that aren't doable by relational machines is doable in trusted polynomial time. We know this. So this probably extends the relational machine class, but we don't know whether it gives you a language in which you can do all efficient computation. What about matching? Right, in my running example, graph matching. Back in 1999, it was posed as an open question whether you can do graph matching in this kind of model. Right? Can you solve it efficiently in this sort of abstract model? Because the algorithms that are known to solve it efficiently are not choices in this sense. And we can actually that it's not. But it turns out it is. It is not only in this, it turns out it's an FPC, and this is something I'm going to advertise this because it's a recent result that appears in the journal of the ACM. In fact, I think it's still the most recent issue. So, how it's done is a bit technical. It turns out it's a very different algorithm to the ones like Edmonds or Zirani. It's done by solving the programming problems, and we show that you can do it sort of in a symmetry respecting way based on something that's on the other side. Okay. Another sort of result of the symmetry that I want to sort of highlight is it's sort of classical tool for studying complexity of problems is to look at the combinatorial problems through properties of circuits. The circuit is simply just an unfolding of an algorithm. Once you fix the input size, you unfold it into simple actions such as boolean and or not. This is again very low level of abstraction. And so then we ask, what about if we want the circuits, consider this low level to be symmetry preserving? We can define them where symmetries of the input have to be also give you symmetries of the action of the algorithm. And we show that things that we can then do efficiently in this symmetry preserving way turns out to be exactly the thing we can do efficiently on the relational machine model. Okay, so it turns out this gives a nice sort of combinatorial way of saying what things are symmetry preserving, what algorithms are symmetry preserving in this sense. Okay, without getting technical, I thought I'd mention this simply because among people who work in complexity theory, this has been big news recently. Right, there's a major breakthrough in the study of one of the classical problems of complexity theory called the graph isomorphism problem. This is the problem of determining, you're given two graphs and you want to say, are they really different representations of the same graph? Which really means can you reorder the vertices of the two graphs in such a way as to make them identical. It's essentially a question about identifying what the symmetries are in a graph, in the sense I've been talking about. Okay. If you don't see that it's essentially the same problem, I think you can easily explain that to you offline in a few minutes. The graph isomorphism problem is one which is not to be handy, and it's a long-standing open question whether it admits efficient solutions. Is it in the class D? We still don't know the answer to that, but recently Babai has shown that it is nearly by a sort of stunning algorithm, which appeared within the last 2-3 months, I would say. Okay. So all this, and I'm going to wrap up now. All this is the context in which I said considering this new project I'm working on, is to say there is a rich theory we have of symmetry in computation. There's a number of different strands which are converging on the study of symmetry in computation. I've mentioned a few of them. And there are many more. I mean, there's work on the complexity of constraints abstraction, problems of symmetry, combinatorial optimization, semi-structured data, abstract syntax. Many of these, it turns out the same notions of symmetry pop up in many different places. There are mathematical tools for the study of symmetry based on group theory, which all seem to pop up in many of these things. And this is what's leading us to focus on a project on symmetric computation. So, which I think is sort of exciting emerging field, which deals with abstraction and complexity, which are the long-running themes in theory of computer science. And hence the title of my talk was Abstraction, Symmetry, and Complexity. But I'll stop here for now and take questions.
Any questions?
So the lower one for the symmetric circuits went to logic, right?
Sorry?
Do you think that's also like some purely circuit complexity theoretic way to get a lower one based on the computer access?
Yes. Sorry, I think I missed the beginning of that. So you're asking apart from, you're asking about how to prove lower bound.
Because you're in the working level, a higher abstraction.
Yeah.
Is it hopeless to think that there is a lower goes through the standard circuit complexity theory.
Right. So is it all? Well, that was part of what we were trying to do in this stuff over here.
Yeah.
Is to tie the high level with the low level. And what ties it is this isomorphic symmetry. So you get circuits, but then you impose that the circuits have got a certain symmetry with them. And then it turns out that they are closely tied to expressive power of these higher level formulas.
So one of the abstractions from computing, which is church, is the lambda calculus.
Right.
So that also means some kind of abstraction of the programming motions of architecture.
Yeah.
Is there a relation between what you're doing and the programming language?
One of the things I mentioned here right at the end, I don't, the sort of lambda calculus is not really my field, but I mentioned abstract syntax here, precisely this reason, that, say, one of the concerns people have had, say, in the study of lambda calculus is there are certain arbitrary notions like alpha conversion, right? Renaming, replacing the name of a variable by another name shouldn't change the meaning of a program. And so that's sort of, you want to abstract away from actual names, and there's been recent work on nominal computation which does that. And it turns out that basically, it turns out to use methods from symmetries, which are very similar to what we've been looking at in this other topics, circuit complexity, etc. So that's why I kind of said there are many different areas we've been converging on study of symmetry, which is a common theme that I want to highlight.
What's your opinion about P equals NP?
What's my opinion about it? No, I think they're different because I think we are very clever at coming up with algorithms, right? We are very poor. We really don't know how to prove lower bounds. If it was a case of P equals NP, we would have come up with a fast algorithm for NP problems by now. It's proving impossibility results that we really don't know how to do. And so that's probably where our gap in our knowledge is. So that's the reason why I think it's more likely that P is different from NP than the other one.
While previous speakers spoke about relaxing assumptions from the model to continue to break the research, this talk speaks more about getting abstractions.
Right.
How would you comment on that?
I'm not.
Well, drop the assumptions and create the abstraction.
That's right. I think creating abstractions is pervasive in computer science. That's what the subject is about. Okay. I think even formulating the assumptions to see which ones you drop is an act of abstraction. So I think that's yes. I think this happens everywhere.
So are there cases where the lack of symmetry is actually useful to understand?
Well, yes, because look, I showed you that we came up with a way of doing graph matching in a symmetry preserving. This is not, this is a theoretical result. It is not the most efficient way to do graph matching. Right? The mechanical algorithm is certainly faster than this. And it does it by breaking symmetry. Right? So it's clear that there are instances where you have to break symmetry. Well, have to I can't say because that's another impossibility result that I don't that we don't know how to prove. But it's clear that there are algorithms where you break symmetries. Essentially, you break the level of abstraction you intend to work on in order to make it.
that's I mean,
So
that's also a trick that we have to have in our bag.
that's right. That's right.
Are there other questions? Great, let's thank
So, thanks everyone for staying through the whole day ceremony. And at this time, we would like to really thank the local organizers. And I think they put up a great show. Unfortunately, Sabu had to get out of his home. There was some call from his home, his son got into an accident. But let's put a big hand for Sabu and his whole team. I would like to invite anyone from the local ACM chapter in and around. Maybe you want to come over. So, because Sabu is not there, you're like a proxy for Sabu. So, let's thank the local organization. He actually is not local, you know, he's proxy. And on behalf of ACM India, I would like to thank the ACM HQ representatives. Let's start with Alex. Can you come over, accept a token. And I'd like to invite Jennifer, if you want to give a token of comment on our behalf.
Oh, I'm looking. Oh, okay. Okay. Thank you for organizing. Thank you. Oh, okay. Okay. Yeah, thank you very much.
Bobby. I would like to thank two more people who have really worked hard for the other part of this program, the IRIS, Professor Bala and Professor Naveen. If you could come forward, except for they have done a marvelous job of conducting this over the past few years, and it's actually a great contribution to the research community. So on behalf of ACM India, we'd like to thank you all. Look forward to seeing you all in Calcutta next year. We'll be publishing the dates. And thanks. Anything else you want to add? Okay. Thank you.